In our on-command, on-demand world, information really is just everywhere. It's the lifeblood of our digital lives, isn't it? From scrolling social media feeds to running critical business operations. But have you ever stopped to think about the invisible symphony playing behind every click, every bit of data, making it all instantly available?
It's quite something. It's all
Yeah.
powered by these huge interconnected data centers, mostly hidden away from our view.
Okay, so let's try and pull back the curtain a bit today. We're doing a deep dive into the foundational architecture of these absolutely essential data centers. We're focusing on a key lesson from our source material on data center environment, specifically this core trio: application database management system, or DBMS, and the host, which people often just call compute. Our mission, really, is to demystify these three, explore what they do individually, and crucially, how they perform this seamless dance together, sometimes in quite surprising ways.
And what's really fascinating here is that while we interact with information constantly, we rarely think about the intricate layers working together behind the scenes to deliver it. Understanding these fundamental building blocks is, well, it's absolutely essential for grasping the bigger picture of IT infrastructure. And honestly, even just for appreciating the magic behind your everyday tech use.
Exactly. Our source material really backs this up. It highlights 5 core elements crucial for any data center to actually function: application, database management system, DBMS, host or compute, network, and storage. But for our deep dive today, we're really honing in on those first three: application, DBMS, and host. You could maybe think of them as the brain, the meticulous librarian, and the tireless powerhouse, all working in perfect harmony.
And that harmony is just critical. I mean, while these three elements are often managed as separate things, they must integrate perfectly to handle the complex data processing demands we see today. Think about an online order system, for example, a really common one. The application is what you interact with, right?
Right.
It's to place your order. The DBMS, it meticulously stores all the order details, your name, address, what you bought, and the host is the powerful engine, the computer, where all this processing actually happens. It runs the show.
That's a perfect way to picture it. Let's maybe trace that online order flow you mentioned. When you, the customer, click submit, the journey starts from your machine, your computer or phone. It connects over your local network, maybe your home Wi-Fi, or even across the internet, the WAN, to a host somewhere in a data center.
Mhm.
That host is running the specific order processing application. The application then needs to talk to the DBMS to pull up your info or save the new order details like your name, address, payment method, the products you pick.
It needs that data.
The DBMS then tells the host's operating system, okay, write this data or read that data to the physical disks in the storage array.
In connecting the host to that storage, that's where the specialized storage networks come in. They're like the high-speed communication highways.
So yeah, while all 5 elements, application, DBMS, host, network, storage, are involved, you can really see how central that core trio is to the immediate transaction itself. All right, so let's kick things off properly with applications. What exactly are these computer programs? What's their role in providing the logic for computing operations inside a data center?
Well, at their core, applications are basically the software that delivers the specific function you or a business actually needs. Our sources break them down into a few broad categories. You've got your business applications, think email or ERP systems, enterprise resource planning that manage, all aspects of a company,
Mm.
or DSS, decision support systems, which help with complex analysis.
Okay.
Then there are crucial infrastructure management applications keeping the lights on, basically.
Mm.
Data protection applications like backup software, super important. And absolutely vital security applications, authentication, antivirus, that sort of thing.
Okay, so that makes sense. But this raises an important question, I think. Why do these applications matter so much for something like designing the storage system? It seems a bit removed, doesn't it? It's not just about what the apps do, is it?
No, not at all. It's profoundly about their I/O characteristics, input, output.
Ah, okay.
Think of it like designing a highway. If you know most of the traffic will be small, fast cars constantly changing lanes, that's like random small I/O
Hmm.
operations. You design the road differently than if it's mostly slow, heavy trucks moving in a straight line that's more like sequential, large I/O.
Right, different needs, different design.
Exactly. The way an application reads data, writes data, and processes it directly dictates the performance needs of the entire storage system. It impacts everything from what kind of disks you buy to how much network bandwidth you need between the servers and the storage.
And our sources highlight those specific I/O characteristics to watch for. Is an application read versus write intensive? I mean, is it constantly pulling information out or mostly putting new stuff in? Is its data access sequential versus random? Does it read things in a nice, predictable order, or does it jump all over the place on the disk?
Crucial distinction.
And what about the I/O size? Is it moving these massive chunks of data in one go, or lots and lots of tiny little bits? Understanding these is really key to building an efficient digital highway, as you put it. Now, here's where things get really interesting and maybe a bit surprising for some listeners. Application virtualization.
Yeah, this is cool stuff.
This isn't just, running your app on a virtual machine like we might think. This is about completely breaking the direct dependency between the application and the underlying operating system and hardware it usually needs.
Exactly. Application virtualization offers some truly compelling benefits. It's really changing how software gets deployed.
Yeah.
First, you get this incredible encapsulation. The application and all its required OS bits and pieces are bundled together into an isolated, self-contained, virtualized container.
Okay, like a little package.
Precisely. And that leads directly to amazing deployment flexibility. You can deploy these application packages pretty much anywhere without having to make fundamental changes to the underlying operating system or the file system, or even messing with the registry.
That sounds much easier.
Oh, it is. Plus, the isolated environment gives you fantastic protection. It safeguards the main operating system and other applications from potentially getting corrupted by a misbehaving app.
Damage control.
You got it. And finally, it's a dream for conflict resolution. It eliminates those really frustrating clashes you get when you try to install multiple applications or maybe even different versions of the same application on one computer. It just works.
Okay, that makes a lot of sense. So next up, let's talk about the unsung hero managing all that data, the database management system, or DBMS. So for those of us who aren't database administrators, what exactly is a database in this context, and what's the DBMS really doing behind the scenes?
Well, a database is essentially a highly organized collection of data. It's usually structured in logically organized tables that are interrelated somehow. Its whole purpose is to optimize how that data is stored and, just as importantly, how it's retrieved.
Making it efficient.
Right. The DBMS, then, is the software that controls everything related to that database, its creation, its ongoing maintenance, and how applications actually use it. When an application needs a piece of data, say, your order history for that online store, it doesn't go rummaging through raw files on a disk.
No.
No. Instead, it asks the DBMS. The DBMS processes that request, figures out where the data is, and then instructs the operating system to find and transfer the exact data needed from the storage. It's like the traffic controller, ensuring data flows efficiently and accurately.
So in essence, you, the user, you're always interacting with the data through those applications we talked about earlier. And the DBMS is the invisible maestro, the conductor, orchestrating the whole process behind the scenes, making sure the right data is there exactly when the application and you need it.
Perfectly put.
Now, let's shine a light on the final pivotal element of our core trio, the host or compute system. These are the tireless workhorses, right? The actual computers where all these applications and databases run their operations.
Exactly. And these hosts, they can be physical machines, the actual hardware boxes you might see in a server rack, or they can be virtual machines, which are basically software-based representations of a computer.
So like my laptop is a host.
Absolutely. Think desktops, laptops, those powerful servers, sometimes huge clusters of them in data centers, and even your mobile devices. Each one at its core functions as a host. And a host isn't just an empty box. It's a complex interplay of the CPU, the brain, memory, various I/O devices like network cards and disk controllers, and a whole suite of crucial software components that allow it to function.
Okay, let's dive into those software components then. The first one, perhaps the most familiar, is the operating system, the OS, Windows, Linux, Mac OS.
Right. In a traditional setup, the OS is the master controller. It's the essential go-between, the intermediary between your application and the physical hardware. It provides vital services like accessing data on a disk and managing all the hardware resources, who gets to use the CPU when, how memory is allocated, etc.
Got it. The boss.
Sort of, yeah. But if we connect this back to virtualization, this is precisely where things get shaken up. In a virtualized compute environment, a thin layer of software, often called a hypervisor, slips in between the operating system and the actual hardware.
Ah, okay, a new layer.
Exactly. Now, the OS acts more like a guest. It focuses primarily on interacting with the applications it's running. The hypervisor, meanwhile, takes over the complex job of managing the underlying physical hardware and cleverly allocating resources, CPU time, memory, network access, to potentially multiple virtual machines running on that single physical box.
That's a fundamental shift in how compute resources are managed, isn't it?
It's huge. Massive efficiency gains.
Okay, then we have device drivers. You mentioned these briefly. What are they exactly?
Think of them as universal translators. They're specialized little pieces of software that allow the operating system to communicate effectively with all the different hardware devices connected to the host.
Like a printer or a mouse.
Exactly. Or, critically for our discussion, a disk drive or a storage controller. Each driver is specifically designed for a particular piece of hardware and a particular operating system. A Windows driver for an HP printer won't work on Linux, for instance.
Makes sense. Hardware dependent and OS specific. Okay, let's unpack another real workhorse, especially for storage management. The Logical Volume Manager, or LVM. You said it's often integrated right into the OS.
Yeah, often it is. The LVM is a really powerful tool. Its main jobs are to optimize storage access and, crucially, simplify management by abstracting away or hiding the nitty-gritty physical details of the disks, where data actually lives.
Okay, but this raises an important question. Why is hiding those physical details so beneficial? What's the big advantage?
It's revolutionary, really, because it allows administrators to dynamically change storage allocation. They can expand volumes, shrink them, even move data between different physical disks while an application is still running.
Without taking things offline.
Exactly. Imagine needing to add more disk space to a critical database server. With LVM, you can often do that without any downtime for the users or the application. That's a massive win for keeping businesses running 24/7. It takes raw physical disks and presents them to the OS as these flexible, logical storage units that can be resized and managed much more easily.
Okay, I see the power there. So LVM manages the volumes. What about the files on those volumes? That brings us to the file system, right?
Precisely. The file system is that hierarchical structure, folders within folders that organizes all your files. It's the system that allows you and your applications to easily find and access data on a disk or a logical volume. It provides routines to control file access, letting you create, modify, or delete files without worrying about the underlying disk blocks.
Like Windows NTFS or Linux XT4?
Those are perfect examples. A key aspect here is how file systems organize data, typically using directories or folders, and they maintain a sort of pointer map or index to where everything is located. The smallest chunk of data the file system usually works with is called a file system block, which corresponds to a contiguous area on the physical disk or logical volume. It's like a library's catalog system, telling the OS exactly which shelf and which spot holds each piece of data or file segment.
Wow. So to truly appreciate the complexity behind just saving a simple file, maybe we should walk through that mapping process you mentioned. It sounds like several layers are involved.
Absolutely. It's quite a journey. Let's trace it. 1, files are created and managed by you, the user, and your applications. That's the top level.
Okay, my document.
Those files reside logically within file systems like NTFS or XT4.
Yeah.
3, the file system maps your file's data into one or more file system blocks.
Right, breaking it into chunks.
4, those file system blocks are then mapped to what are called logical extents within a logical volume. This is where the LVM often comes in. 5, the OS, or the LVM, then maps those logical extents down to the actual disk, physical extents on the underlying physical drives.
Getting closer to the hardware?
6, and finally, those physical extents are precisely mapped to the actual disk sectors on the physical storage device itself, the spinning platters or flash cells.
Phew. That's quite a stack of translations. It really highlights how much abstraction is happening to make it seem simple to us.
It's essential complexity, managed seamlessly.
Okay, here's where it gets really interesting, again, tying back to virtualization. Compute virtualization. You mentioned the hypervisor.
Yeah.
This isn't just a minor tweak, is it?
No, it's a breakthrough technique. It fundamentally abstracts the physical hardware, the CPU, RAM, network cards, away from the operating system. The magic is that it allows multiple, completely isolated operating systems to run concurrently, side by side, on a single physical machine.
Multiple OS on one box.
Yes, and what's truly fascinating here is how this creates these portable virtual compute systems we call virtual machines, or VMs. Each VM acts like its own complete self-contained computer. It runs its own operating system, could be Windows on one VM, Linux on another, and its own set of applications, all in perfect isolation from the other VMs on the same physical host.
And the hypervisor is the
The
key.
hypervisor is the magic layer we mentioned. It sits between the hardware and the VMs, providing each VM with virtualized resources, a virtual CPU, virtual memory, virtual network connections. It manages the sharing of the physical hardware among all the running VMs. It dramatically increases resource utilization and flexibility in the data center. You don't need a separate physical server for every single OS instance anymore.
Incredible efficiency. And that leads us finally to desktop virtualization. How does that fit in? Is it just running Windows in a VM?
It builds on compute virtualization, but takes the concept even further, specifically for user desktops. It breaks that traditional tight one-to-one link between your operating system, your applications, and your user profile, and the specific piece of hardware sitting on your desktop PC or laptop.
Okay, so decoupling the user's environment from their physical device.
Exactly. If we connect this to the bigger picture, the idea is to host all those individual user desktops as virtual machines running centrally in the data center. Users then access their personalized desktop remotely, often using thin devices.
Thin devices.
Yeah, these are typically very simple, often low-cost computers or even tablets or repurposed old PCs. They don't do much processing themselves. They mainly just display the screen image being sent from the VM in the data center and send back keyboard and mouse inputs.
Ah, so all the heavy lifting, the application execution, the data storage happens back in the data center.
Precisely. And this offers huge benefits for organizations. It massively mitigates risks like data leakage or theft if a laptop is lost or stolen, because the data isn't actually on the device. It also dramatically simplifies compliance efforts. And think about patching, updates, or rolling out new applications. IT can manage it all centrally on the VMs instead of touching hundreds or thousands of individual PCs. It's a huge win for security, manageability, and often cost efficiency in the enterprise.
Wow, what a journey we've taken. We've really done a deep dive into the application database management system and host or compute elements. These things form the very backbone of a data center. We went from understanding what these fundamental components are to how they intricately interact, and even how concepts like virtualization are fundamentally transforming their very nature.
Indeed. We've seen how applications, drive the need for organized data storage, how the DBMS acts as that crucial intermediary, the guardian of the data, and how the host system, with all its complex layers, OS, LVM, file systems, provides the powerful platform for everything to actually run. I think the aha moment, if there is one, really comes from understanding that these aren't just separate boxes or pieces of software. They are deeply, intricately interwoven layers of abstraction, each playing a vital role in this grand, invisible symphony that powers our digital world.
Yeah, absolutely. And the surprising facts about application compute and especially desktop virtualization really highlight how IT infrastructure is constantly evolving. It's always striving to become more efficient, more flexible, and maybe surprisingly almost invisible to the end user when it works well.
hmm It makes you think differently about the digital world, doesn't it?
It really does. So thinking about our listeners, what does all this mean for you as you navigate your digital life every day?
Well, this raises an important question perhaps for you to mull over. How might understanding this incredible abstraction, this interconnectedness of these core data center elements, especially when you see it through the lens of virtualization, how might that change the way you interact with, or maybe even design, any digital service you use, whether it's your favorite streaming app or a massive global enterprise system?
It really makes you appreciate the invisible ballet happening behind every single click, every search query, every shared photo. It's quite a testament to human ingenuity, actually.
It truly is.
Thank you for joining us on this deep dive today. We hope you feel a bit more well-informed and maybe even more curious about the amazing digital world that surrounds us.